Okay, does everyone have slides open? Very good. Okay, so yeah, this is going to be a little bit funky. So please, if you feel like you're getting lost because I can't really navigate this, just let me know. We'll try to make the best out of this situation. Okay, so as I said, welcome back. I see some happy notes about your spring break, which makes me really happy. I have just shared this morning your grading for the midterm exam. You have a week to check it out and see whether there are any mistakes. If so, please open a regrading request on Gradescope and we will immediately check that out. This week, we also expect to finalize grading of the third homework so you can get a better sense of where you are in terms of the grading. I will talk a little bit about the midterm feedback, and but before that, I just want to highlight the two NLP talks that are happening this week. On Wednesday, we will have Swaba giving a talk at the data science seminar, which is in this Gardner Commons building, so not Mab or Web. I suspect this to be a great talk. You should all attend if you are interested in large language models. And on Friday in MEB's LCR at 11 a.m., Zhao Feng Wu will also give a talk related to LLMs. I work both with Swaba and Zhao Feng. I know them very well, and I expect these to be great talks. So if you have time, I really recommend attending them. Also forgot to add here, I sent an announcement about that in Piazza this morning. There is ACM Club kickoff this Thursday. So if you are interested in joining that, yeah, there are information on the flyer. And it's a great way to meet other students and have a little bit more of sense of community, which is sometimes a little bit lacking at University of Utah because it's a commuter campus and then you don't get to see each other as much as, in other schools. Okay, so let's just briefly talk about the midterm feedback. Thank you. Thanks to everyone who has submitted your feedback. I really appreciate it. This is super helpful for me. And amongst things you like course content, which is not surprising because it's very, cutting edge, large language models. Everyone wants to know more what this ChatGPT kind of thing is. So I can't, it's not me. It's the content that's really rewarding. You like that there are office hours, materials, and a lot of you actually said you like homeworks, which I was like, okay, cool, that's good. There's, a substantial amount of you who actually appreciated them. There is a few of you who also said there were some issues with homeworks, and I do agree with that. Maybe something I didn't mention is that this is the first time I'm teaching this course, so some things are definitely, rough around the edges. I do agree that more guidance on the hyperparameters would be really appreciated because it kind of gets a lot of time to find those. I do want to emphasize, oh yeah, please. Are you fine with me talking while you do that? Okay, perfect. I want to emphasize that finding hyperparameters is a huge part of your job as a person who's training these models. So it's not, if you're feeling frustrated during your homeworks, trying to find the right hyperparameters, that's how you're gonna feel when you're training these models. It is annoying and frustrating part of training models, as well as debugging. A few of you asked me, like, how can I know whether I have a bug or I'm having misunderstanding of a major concept? One suggestion I gave in office hours was to try to overfit on a batch of data. So pick one batch of data, a few instances, and just keep training on it. If you don't achieve like very low loss and very high accuracy of that single batch, oh, great.
I just made sure it was turned on, but I tried my adapter. You want to try yours real quick?
Yeah. So now it works.
Yeah, I think it seems like it's fine. It might be this adapter might be better.
Yeah, I tried to. Maybe I can buy the one you have.
Yeah, if that one ends up being one that works, let's use that one.
Yeah. I tried this other one as well.
Right. Yeah, let's just
okay.
So yeah, you can hold on to that, and I believe they gave us your UID already.
So I just returning.
Yeah, the end of the semester if you
okay, great. I'm a queen of adapters. Thank you.
Yeah.
All right. Yay. I feel better.
Yeah. Okay.
Yeah. Thank you. Okay, great. So yeah, I was saying that you should overfit on a batch of data. If you cannot overfit on batch of data, that likely means that you have a bug in your code or something is not right. Like you should be able to, with a neural network, you should be able to memorize that one batch of data. So that's a good check. And then if you are overfitting on the batch of data, but you still don't get good development accuracy, that could be the sign of needing to do hyperparameter tuning. So that would be the next thing I would do. If you are not overfitting on that batch of data, you suspect you have a bug, it doesn't necessarily mean you have like major misunderstanding of the concept. It can be that you misread the documentation of Torch. For example, we have seen with the Torch negative log likelihood that you need to give normalized logits, while with cross entropy in Torch, you had to give unnormalized logits. And these small differences can throw off the whole thing, right? So what I would usually do, I would go like line by line, check the shape of tensors. That also gives away a lot. And just see like, you know, inspect the tensor a little bit, see whether the values are fine, and then do line by line while simultaneously doing this like computations, maybe by paper or by hand on paper, just checking whether I'm doing the layer combination that I really wanted. So in the end, it's a lot of like, you know, manual and boring and tedious work, but it is really how it is in practice. It's not always just smooth sailing where with pre-trained models is less finicky, but even with them. So, you know, it is, I'm sure, hard to accept that frustration around this. It's valuable, but I hope to some extent you can accept that. Yeah, there was also like, I want to explain, I did this, explain this in maybe in office hours, but not to everyone. The reason why I don't you to, for us, me and TAs to look at your code directly. And the reason is that that quickly turns into just giving away solution. It's really hard for instructors to just not be like, change this, you know, like you just want to jump to that one thing. And that prevents you from, you know, doing this practice of debugging, which is really important to understand. And it becomes very unfair because if you don't come to office hours and we don't give you away this very strong hint, then you are, yeah, there's definitely you are behind than people who got that hint. So the do here, it's hard to how to give like feedback, but not look at the code. And that's something for me to think about how to do in the future. I think like more relevant details in lectures, all of those things can be better connected in future lectures. So yeah, thank you for that feedback. It's really useful for me when I teach this course again in the fall to kind of integrate these changes. And yeah, you mentioned that sometimes it's hard to digest the topic, and I can see that. That's also something to navigate as an instructor, and like having some kind of practice problems could be useful. I have this in mind, but I do make like 60 slides every week. So it's like, you know, like these are all the things I'm like, yeah, these are great things to add, but I can't promise they're going to happen this year, but still want you to kind of acknowledge that that's a good feedback. Any questions, anything extra you would like to raise for the rest of the semester, for a few more weeks we have together in this classroom? Okay, if something else comes to mind and you don't feel like confident saying in the classroom, but now it just came to you that we could do something different, shoot me a message over Piazza, and happy to chat more about it. All right, so I'm sure you're interested in projects. I promise I will talk about them at the beginning of the next lecture. There are a few more things I want to clarify to myself, so I will not talk about them today. Please be patient, and then I promise on Wednesday I will tell you everything you need to know about the projects. All right, and now so in the following few weeks until April, we're going to take a little bit more, I would say, standard, like before LLM's standard NLP pipeline. We're going to take a look into it. And, you know, I think for a lot of you, the question is, why do we need to know about about this standard NLP pipeline now that we have learned about large language models, that we can fine tune them for many tasks, many applications, and so on. And there are, I mentioned this in the introduction lecture the first time we met, and I just want to go over some of these arguments very quickly. I said that knowing about linguistic structure prediction, meaning trying to, automatically find some kind of structures from text, can be useful to think about the second question that I mentioned is relevant for NLP, and that's understanding human language, using computational methods to learn more about our language and theories behind it, or, develop new theories. And we said that there is this very big discussion that's going on in the NLP and therefore the AI community of whether these models can understand and reason. And one way to kind of address this question is whether they can, whether they are also able to do these kinds of, build these linguistic structures. And this question is at the core of what AI is. I gave you this little digression of what AI is, and we said like AI was coined in the 50s, and it was this aspiration to, realize in software and hardware an entity that possesses like human level intelligence. So it should be like high level or cognitive capability of humans to reason and think. And we said the capability of language, of speaking and reasoning in language, not necessarily speaking, sorry, that was wrong, just reasoning in language is one of the central features of human intelligence. And reasoning is central for many tasks in NLP, such as reading comprehension that we mentioned a couple of times. So if you really want to know whether these models can reason, we do need to dabble a little bit into linguistics, understand what does it mean to be able to reason and think. So having knowledge about what linguistic structure prediction means is useful to think about these bigger questions. I also said that, right now we are modeling about 100 languages, and there are over, here this slide says 6,400, but there is actually over 7,000 languages. And we have mentioned that many of the languages that have been modeled are in specific geographical areas. And for other areas and for languages in those areas, we actually don't have any text. So not like labeled, human labeled text, but rather no text at all. There is no way to just scrape it and take it and then build a large language model over it. So for many, many thousands of languages, you do not have a chance to have a strong large language model, and you're better off building more traditional NLP models for those languages. So maybe those are your interests. Maybe you are interested to, contribute to those languages, and then things we are going to talk about in the following weeks will be very useful. And I also mentioned this problem of citational amnesia in NLP, that papers, like researchers are stopping to cite and properly attribute older works, and there is this, reinventing the wheel kind of situation. And you should be knowing whether whatever ideas you have, whether they have been already discovered before. So there is also some due diligence here. Related to that, I think these things we are going to learn about, it would be honestly embarrassing if you don't know about them. If you go to an NLP conference and someone mentions, oh, I work on co-reference resolutions, and you're like, what is co-reference resolution? They will be extremely confused how you don't know what that is, because it's like a very important task in NLP. So I think it's very important to, although you might not approach it in this, non-LLM way, I think it's still very important to be aware of that. So with all of that, I want to move into one of these linguistic structures. Any questions about anything I said so far? Yeah, and once we are done with this, in April, we're gonna return to large language models a little bit more. They're going to talk about how do we build these multilingual large language models, just like briefly, like 40 minutes of that, 40 minutes of like how to build multimodal large language models. We are going to talk a little bit about responsible NLP, fairness, and how to do explainability. So we are going to go back to large language models and finish on that note. Okay, so first thing I want to talk about is part of speech. Part of speech and the task of part of speech tagging. Part of speech are categories of words based on their grammatical role or their morphological properties about their affixes. Morphological, remember, refers to kind of how we change the words by inflecting them and, adding prefixes and suffixes. And affixes are just a single word to say prefix or suffix. So you are categorizing all possible words depending on these properties rather than their semantics, right? Like we had talked about synonyms and antonyms and so on. That's not what we are doing here. We are looking at their grammatical relationships. And to do that, it's important to know there are two types of words. There are so-called closed class words, which have, we say like fixed membership, meaning that, let's say, pronouns, we are not adding ton of pronouns often to the set of pronouns in a given language. So they're kind of changing slowly or not changing at all. And very often these are function words, short, frequent words with grammatical functions such as determiners, pronouns, or prepositions. Other classes of words, and here, if there is a very fixed grammatical membership, then yeah, you know how to assign it right away. Like there isn't anything ambiguous about what's the role of that word in a given sentence. So the assigning the part of speech tag, although I didn't explain what are the possibilities for the part of speech tags, but it's going to be, you can use a rule-based solution. However, there are open class words which are continuously being created or borrowed, such as nouns, verbs, adjectives, adverbs, and interjections. I recommend, and not only that I recommend, I require that you open Jurafsky and Martin's chapter 8, these pages 2 and 4. You're going to find there a list of words, types, such as, definition of what a noun is, or adverb, or interjection, but also conjunction or copular models. And these are all terms you want to be aware of. Like if someone says, oh, this is a modal verb, you should know what the modal verb is. And it's not useful for me to now go over definition of, 20 word types. That's going to be very boring and you're not going to follow. But I do want you to do that because, again, this should be part of your vocabulary when you talk with NLP people. So with part of speech and part of speech tagging, assigning part of speech types to words, there are some ambiguity. It's not one-to-one membership. So here on the right, I am giving you a list of possible part of speech tags from Pentry Bank. Pentry Bank is a corpus that comes with these human annotated labels of part of speeches. So we have CC, coordinating conjunction, CD, cardinal number, and so on. All right, let's try to do this together. Let's start with the first word I. So I know it's a pronoun. So because this is comes in an alphabetical order, I will find pronoun. Well, I should be finding quicker. Here it is. Personal pronoun. It's 18. So I'm assigning IPRP tag. Okay. Will is a little bit tricky, so I'm not going to ask you. I'm not sure which tag here exactly annotator would place because there isn't. It's not 100%. It could be a modal verb or just a verb. I'm not sure. How about book? Which tag would you give a book here? Maybe someone can raise a hand. Yeah, please. Verb. In this sentence, it is a verb. Yeah, VB, and then we have different options for VB, and this is the base form. I did hear some nouns, and that's great. That's what I want you to achieve here. I wanted to show you that there is ambiguity, right? Like this could be a noun or a verb. So here we have determiner, room, noun, at. Yeah, and there is a special tag called in. Let me just find it. Here, preposition. So it's a little bit, also you need to figure out what kind of, you all said preposition, but like how do we, what the actual name of the tag is, it's good to know. And then we have determiner and again, noun. And now here in this different example, we have book, but book here is a noun, right? So that's what already happened when you were trying to do this and, you maybe didn't read the rest of the sentence and you got confused by a noun or a verb. So assigning part of speech tags comes with some ambiguity and you can't use some rule that assigns a given word one tag all the time because that's not going to be right always. Okay, so this task that we have just been doing ourselves is called part of speech tagging. It's a task of assigning a part of speech tags to each word in a text. So the model gets a sequence of units. And for the sake of this lecture, I'm going to talk about words. You can also think about tokens if you like and subwords, but just for simplicity, words. They're going to be tokenized and you need to give a tag set. So you need to give a list of possible part of speech tags. The one I have shown you here comes from Pentry Bank. So you have this list of possible tags. And let me just skip to this one. There is another set of another tag set that people have proposed. This one comes from universal dependencies. So if you were doing part of speech tagging, but with the tag set in universal dependencies, you would assign different tags because the output space is basically different. So you need to give a tag set. And then the output is going to be for each one of the units, for us words, you are going to give a label. So each one of the words, one by one, gets a label from our tag set, just as we have done it as an exercise on a previous slide. This is an example of sequence labeling or a sequence tagging. These are the family of tasks where you need to assign a label to each unit in a sequence. And in this way, what you are kind of doing then is providing a mapping between a sequence of units, words, to a sequence of labels. Part of speech is not the only sequence labeling task. There is many of them. And you need to remember this is like a new type of task, different from, let's say, classification, where you just had, for a single sequence, you had a single label assigned to it. So sequence labeling, important term to remember. Why do we care about part of speech tagging? It can be useful for other NLP tasks. For example, if we are doing parsing, we are trying to build some kind of syntactic structure of the sentence, something we are going to talk about next week, then providing part of speech can be useful. For example, whether a verb is a noun or a verb, tell us about likely neighborhood words, such as nouns in English are preceded by determiners and adjectives, verbs by nouns. So that helps you with the, when you're building syntactic tree, you need to know which words have, connection to each other. And you would under your model, you will more likely put a connection between verbs and nouns. I already said this, it's useful for reordering of adjectives and nouns for machine translation. So, for example, if you have a machine translation system from Spanish to English, then it might be useful to know that in Spanish, adjectives come after the nouns, where in English they precede the nouns. So if you knew the word is noun and you knew this rule, you can introduce this rule to your system such that your translation in English is such that the adjectives come before the nouns in your translation. But you need to know whether something is adjective and noun to be able to deploy this rule. There is a task where we want to, in sentiment classification, we want to maybe you know, find out what are the adjectives in the review, and then maybe we have a lexicon with sentiment, positive and negative sentiment words, and then we can assign positive or negative sentiment label to each one of these adjectives if they appear in our lexicon. And in this way, we might get a very strong baseline of whether something is positive or negative. Maybe we just average how many, if there are more positive adjectives, we say, okay, this is going to be positive. And then for text-to-speech application, it might be useful to, when there is ambiguity in how we pronounce certain words, like lead, we can read it as lead or led, object or object. If you knew whether something is a noun or verb, you can provide more precise pronunciation, right? So for different tasks, this comes in handy. And of course, you know, like you can default now, well, I have my large language models and I don't need any of these handcrafted features. And you wouldn't be wrong if you're thinking about very high resource language like English. But then, as I said, there are thousands of other languages where you don't have that option. And there you might be interested to deploy part of speech tags that is a part of your input feature set. Also, when you're doing like stuff like cultural analytics, you are interested, given a large body of text, you're interested to learn something about how people use words or something about that text on its own. You might be interested to, you know, extract nouns or verbs or adjectives to be able to do that analysis of text. So sometimes you simply need to know the grammatical categories of words to do the whatever study you are interested to do. If you have been this morning at the talk by Maria Antonia, you have seen how she studied power relationship between people in stories, especially in stories when people tell their birthing story, and how understanding the grammatical relationship between these entities can help you understand who has more power in this relationship and so on. So if you are interested just to look at the body of text and try to learn something about people from it, you might need to extract categories of words first. All right. As I mentioned, is this convincing? We feel like we need this? Okay, good. Not everyone is nodding, but no one is doing this. Although this means yes in other languages, which I learned hard way. Okay, so I mentioned that there isn't one single tag set for you know, part of speech tagging. This is a Pentry Bank English specific tag set, very common. But I also mentioned there is another one, also common, universal dependencies part of speech tag. And this one will be very useful or state of the art or whatever when we are building dependency parsers, something we are going to talk about next time. So just have in mind that if you see some part of speech tags that maybe you have like learned everything about Pentry Bank tag set, and now someone brings you this one, you should remember, okay, they're just using different tag set. I'm also not expecting you to know all of these by heart, you know, like when time comes when you have final exam, you don't need to know what, I don't know, whatever RB is. I'm not gonna ask you that. All right, so how difficult is part of speech tagging in English? Roughly 15% of word types. I emphasize types here for a reason. Do we remember this distinction between types and tokens? It's okay if not, I mentioned this like once. All right, so when we build a vocabulary, then we have a set of distinct units there, right? Let's say words. Those are actually called types, these unique units. And their occurrences in text are called tokens. So when I say types, I just want to say, okay, roughly for 15% of word in the vocabulary, like unique words are ambiguous, such as Janet is always proper noun and hesitantly is always adverb. But those 15% of types occur very often in corpora as tokens. So very small part is ambiguous, we can't always assign the same part of speech tag to them, but they do occur more in the data. So the problem of ambiguity becomes larger than 15%. Is that clear? So when we look at how many tokens in our corpora are ambiguous in some corpus here, then 60% of them are actually ambiguous. For example, type back, we have earnings growth took a back seat, so here adjective, a small building in the back, so noun, clear majority of senators back the bill, so verb, enable the country to buy back depth, and I was 21 back then. Sorry, this is so weird to read when there is this part of speech tag in the middle. So you can see there are different part of speech tags we can assign to this word back. However, not all of these tags for this given word are equally likely, right? So there are different possibilities for part of speech tag of word back, as we have just seen, at least 5, but not all of them are, one of them is more likely than the other. So there is this very important concept in NLP that extends beyond part of speech tagging called majority baseline, where this baseline assigns a label that's most frequent in the data. So for each one of the word, for each one of the types, you're going to find in your corpus what is its most frequent part of speech tag in that corpus. So, and let's say that, I don't know whether this is true, but let's say adjective is the most frequent tag for the word back. And we are going to always assign it adjective part of speech tag, although that's not necessarily true. That's the majority baseline. And you always want to calculate majority baseline when you are introducing a new task or new data set. If your labels are balanced, then majority baseline is basically the same as a random baseline. So you want to include those baselines to give a sense of this is a lower bar. If your model is worse than those baselines, that's really, really bad. So if you do this for part of speech tag in one corpus called the in this corpus over here and specific sections of it, then you will get the performance, the accuracy, which is really high, 92%. And the gap between the part of speech tagging done by this majority baseline and human or state of the art is only 5%. So the ceiling is 90–70% here. So part of speech tagging in English is not terribly hard, which is good if you want to use it as a feature for something else, as we have seen in the couple slides back. We want to use it as a feature for our, whole pipeline to do some more complex task. And that's nice because then we can rely on this feature. What are some sources of information? I'll just quickly go over this. Where those 5% come from, how did we improve on that? We might have built a model that utilize the fact that prior probabilities of wording and or a tag that, for example, will is usually an auxiliary verb, identity of a neighboring words, morphology and word shapes. These are all things that hint on what the part of speech tag is. And standard algorithms for part of speech tagging are supervised machine learning. We might use models we have learned in the first part of the course. We might randomly initialize an RNN or a transformer model and use a corpus where we have sequences of text that are labeled with sequences of part of speech tags. And we might just train the model to, in a similar fashion, we did like language modeling, right? Where you did, in the end, you knew what the ground truth were, what the true word was that comes next was, so you could just use it as a gold label. Here you have different output space, which is the space of part of speech tags, which you have a few dozen, not much more as we had with language modeling, and you kind of do the same thing. Or you can use a pre-trained model. Here, Juravsky and Martin describe BERT as a large language model. I would not call it large, but that changes, of course, right? What is large really is subjective to mean something in the range of, I would say, 10 billion or 7 billion. So yeah, it's a small conundrum of whether we call BERT-like models large or not. But in any case, you can fine-tune a pre-trained language model. However, there are approaches here that do not rely on any kinds of neural networks. For example, hidden Markov models, and that's what we are going to talk about today. Something that just relies on having a labeled set and doing some statistical approach over it. We are still learning some parameters of the model, but there is no neural network, there is no backpropagation or anything like that. All of these models achieve about 97% on English language for part-of-speech tagging. In neural models, we are using representations that are learned, right? Like whatever is the last output in our neural network, the most nonlinear transformation of the input, with hidden Markov models and other non-neural models, we need to craft features ourselves, and we might craft them by using some of these properties I have outlined over here. Okay, so just to kind of recap about part-of-speech tagging, we have learned that part-of-speech tagging, part-of-speech tags are these grammatical rules of each word. And we have introduced the task of part-of-speech tagging, which means that we are given a sequence of text and we are labeling each one of the units, either words or subwords, with its part-of-speech tag. Tags themselves can come from different tag sets, and we have seen that part-of-speech information about part-of-speech can be a useful feature for downstream models, whatever. If our goal is to build a translation system or a text-to-speech system, these can be useful features. And we've seen that also the achieving high performance on part-of-speech tagging is not super hard. Even with non-neural models, we can achieve 97% accuracy, and outcome is that we indeed can use these as features to our whatever model we are building. Okay, any questions? Sorry. Yes, please.
Curious, like how it would maybe work for languages that, for example, like Thai, where words aren't separated on white or by a white space, and like interpretation of a sentence could maybe be like we could introduce ambiguity that way as well.
Yeah, for certain languages, part-of-speech tagging, the way I introduced it with these part-of-speech tags in a given tag set will be even like so limited you can't even approach it in that way. So there is another task called morphosyntactic tagging, when you are for morphologically rich languages, you are including much more, you need to know much more about morphology and kind of even introducing that in the tag set. Now, your question wasn't just about the like those kinds of languages, but also when you can't split them, right, into words.
Yeah, and like then the word boundary is maybe.
Yeah. Yeah, honestly, from the top of my head, I don't know how people approach it. If you are working on a character level, let's say, I will definitely look into it and let you know on Wednesday. Some ideas that come into mind is that, okay, there are these, maybe if we split it into characters, but in the end, there is some learning of the word boundary, and that might not be super easy, but that should happen eventually. And then once you have hit the word boundary, you can combine the information you have gathered so far for a given word to say what is the word's role is in the sentence, what its grammatical role is. Now, some languages don't even have, I think Korean doesn't have adjectives. Maybe I'm wrong, like maybe I shouldn't give an example if I'm not sure, but some languages literally don't have roles that, let's say, English has, so the tag set looks completely different. So everything I said right now is very specific to English, which kind of Now, when I say it defies the purpose of me motivating this as we need, something for these other languages. So yeah, apologies for that. I will look more into it and let you know next time. Okay, so did someone else had a question here? Yes, please.
Like, how does knowing our speech allow us to reason?
How does not okay, so yeah, how does part of speech connects to knowing whether the model can reason? Well, part of speech tagging is part of these. Let me try to find where I introduced this. I mentioned that part of speech tag can be useful for extracting these syntactic structures and the idea of whether we can whether the model can build this representation. So like syntactic representations can be connected to the arguments about whether models reason or not. It's a deep discussion and very detailed. I can't, like, it would take me a super long time, but I recommend going back to, so here, in this slide, you can find more references to these discussions that are mentioning so-called meaning or form debate. And this is where syntactic structure and parsing comes into a play. So for this specific debate. So it's not a super direct connection. Don't try to make like, I have a part of speech tag and now I can answer whether the model can reason and think. It's not like that. It's part of your vocabulary to be able to kind of engage in these conversations and these debates. Yeah. Oh, yeah, please.
So I guess this is a question on what you're talking about with the machine learning and the accuracy of on this slide. That has a performance of 97%.
Yeah.
Is that because of the inherent ambiguity in language rather than failure on the algorithm part?
Yeah, since the human ceiling here is also 97%, it usually means that the remaining 3% are due to some inherent ambiguity, something that even people can't agree with, which can be just coming from, for example, when I showed you example, I will book something. I myself wasn't sure whether I should tag it as a modal verb or just a verb. You need to have a very clear-cut definitions of your tags to have a very good agreement. So it can be just because of that. But if humans have that not 100%, which is very, very often what we see in NLP data sets, then that usually means those extra, few percent, we should not be trying to reach more than the human ceiling. It's usually just mean modeling noise. Yeah. Yes, please.
How species the universal thing among language or just to some like Indo-European language?
Sorry, I didn't quite get your, I thought you were asking something and then at the end it threw me off. Can you repeat your question?
Like, how speech is a universal thing among language around the world?
Okay, so the question is the performance of part of speech tagging for other languages.
Not like just I think it's a linguistic thing. It's like, is it part of speech a universal thing among language or just to specific language?
I see. Okay. The question is whether part of speech is specific to certain languages. And I would say that many languages are structured and therefore there are rules that, words play in grammar of those languages. So yeah, it's a universal concept of like, what is a grammatical role of a word? But the tag set, the set of possible roles words can play differ very much from language to language. As I mentioned, some languages might not have adjectives. That's just not the thing they have in that language. So it's a completely, how is that compensated with other roles might be interesting and so on. So yeah, the part of speech as a concept is pretty universal, but what are part of speech among different languages is not universal. Okay. Okay, let's move on. So the second task I wanted to talk about, which is also sequence labeling task, is named entity recognition. Named entities means anything that can be referred with the proper name. So it's a pretty vague definition. Okay, before I continue, I see my battery is low and I don't have my charger here. Do you have a charger, maybe, Rishant? Or Borvit? You have it. Today is not a technology. Alrighty, so I was saying that named entities it's a vague definition, but basically it's anything we can refer with proper names. So most common tags are a person, of course, location, organization, or geopolitical entity. And unlike part of speech tags, they are where you assign a single part of speech to a word. Here, named entities can be multi-word phrases, which means we have so-called segmentation problem. Given a text, where does the named entity start and where does it end? It's an additional difficulty when we do the labeling. So how do we even do it? How do we kind of signal this is the beginning, this is the end? We use so-called BIO notation that I will get maybe immediately here. So we will have our set of possible entity tags, which again, whoever developed the data set and annotated it, this is where these decisions come from. And the entity tags might be different depending on what you're trying to do. So they can, these are very common ones, but we can have also very abstract ones, such as dates and times and prices. They can be also specialized to a domain. So maybe you are working with scientific text and you want to know, oh, this is a mention of a gene or a protein or a disease. Or maybe you want to be very specific. So you have very fine-grained categories like animal, mammal, dog, and so on. Like you go many levels below just an animal. So you have a data set and you have certain goals. You're interested in certain named entities. You will get whatever possible entity types are. And then you're going to use this BIO notation. It's slightly different. Sometimes people also introduce and S tags, which I'll get into a moment. But for now, focus only on BIO. B stands for the beginning of a span. So for example, here you have possible entity, named entity type being person, but you kind of extend the person set by prepending B or I to a beginning. And then B stands for this is the beginning of a named entity that is of the type of person. And I means this is a word that's inside of the named entity of a type person. And O means, okay, now you are outside. We stop. This is no longer the same named entity. It's not even a beginning of another entity. It's not an entity. Then you move to a next word and you're like, okay, this is an organization. So I'm beginning an named entity of a type organization. Next word is inside of the named entity, which is of the type organization. Again, next word is again inside the same named entity of the type organization. But then you reach the word discussed, which is not named entity, so it's outside. Another word is outside, and then you have a single entity here, which is beginning of location. And now these other schemes just differs on whether you want to, for example, in IO, you don't care whether something is beginning, you just want to say this is an inside an entity. The issue here becomes when you have two entities that comes right after each other, right? Like then you can't separate them. because it would just be inside of a named entity. If they are of the same type, you wouldn't separate them as two separate entities. And this one introduces the end and s. So end says this is the end of named entity, and s is like this is a named entity which consists of a single word. This is too rich, we don't really need it. This is too limited, so usually you will see BIO notation. Okay, so just to be extra clear, we start with a set of entity types. Let's say we are having only person, location, organization, and geopolitical entity. So four entity types. And we decided we are going to use BIO notation for labeling. Then each one of these will produce two possible labels. Begin B-PER, I-PER. So from each one of these entities, we have beginning and inside variation of this entity type, and then the outside label, and this becomes our label set. So from 4 tags, we have ended up with 9 actually labels, 2 per each one of these plus the outside one. Is that clear? Okay, so what is named entity recognition? It's the task of identifying all spans in text that denote some category of entities. And you do not necessarily need to approach it as a sequence labeling, but it's very often approached as a sequence labeling task. Meaning for every single, we are given a sequence of words or tokens, and for each one of them, we are going to assign the label in this BIO notation. Notice that before I said, okay, for simplicity, I'm going to talk about words, and we are assigning each word a part of speech tag. But if we actually have tokens, and we must with, let's say, bird, then you still again need to use BIO notation, because now tokens, subwords are split. One word is split into multiple potentially. And how do you know whether they are, part of the same word? Well, you are going to then do something like BIO notation again. Okay, named entity recognition clear as a task. BIO notation clear. All right, it's a very canonical NLP task, still to this day very active. I will talk on Wednesday a little bit about what are kind of open challenges in this space, even for English, which might be interesting. As well as with part of speech tags, you can't really rely on a lexicon and say, okay, as long as you are this word, you're going to be this entity. Here we have a mention on Washington that can be any of those four common entity tags I have mentioned. It can be a mention of a person, organization, location, or geopolitical entity. As with part of speech tagging, named entity recognition, NER, can be useful to handle other NLP tasks if you are having a pipeline approach. So one task that this is useful for is so-called targeted aspect-based sentiment analysis, where instead of just giving an overall sentiment label for a piece of text, you want to say who expressed what kind of sentiment to what. And this is very common in customer reviews, where you have this user like these aspects of this, I don't know, phone, but they did not like these aspects of this phone. So if you want to do that, then it's useful to know, okay, these are the entities. Some of them are, this is a person, location, and there are these kinds of relationship between them in terms of the sentiment. For question answering, it's useful to know, okay, if you have a question about entity and there is a Wikipedia article that maybe this entity is mentioned in, it's useful for me to know the entity type. Same with information extraction, extracting facts about entities from text. And again, I mentioned that sometimes you don't care about solving the task. You just want this information to do something extra, some analysis. You might not care about solving NER. You just want to extract entities to be able to tell something about a piece of text. Maybe you are interested in a particular, mention how people change, maybe there is a reference of location and person, and you are interested in which period of time people start to talk more about the person than location. I mean, totally made up example. I don't know why that would be useful, but you might just be interested in how usage of words changes and what it can tell you about, people who use these texts. As with part of speech tagging, the tool set you have here is kind of the same. You have you use supervised machine learning, so you have some data where these named entities are labeled, and you are training a model in a supervised fashion. And again, here is the exact same list as with part of speech, and I did promise we're going to talk about hidden Markov models. So that's what I'm going to do next. I just want to recap that, NER is another potential sequence labeling task, where the goal is to label text with respect to whether there is a mention of a named entity or not. And we also want to know the type of the named entity. And because named entities are often multi-word expression, we simply need to use BIO notation, which just tells us when the named entity begins and ends. And we talked a little bit about how it can be useful for other NLP tasks if you are approaching this that task in a more standard NLP pipeline fashion. Questions about NER, named entities? Yes, please.
Done by something. Figure out whether there's any person you talked about.
Okay, so there are a few things here. You could use transformer, but not just self-attention. You need a whole transformer to do sequence labeling. So you can put a sentence into a transformer model, and then for each one of the tokens, you will get a representation, and you use output layer to predict, the label, the named entity label for that specific token. But using just self-attention cannot give you that, right? Like what you get from the self-attention and it depends what you exactly mean for self-attention. Is like overloaded term, but if you are thinking about that sequence length by sequence length matrix, it gives you a relationship between words, but it doesn't give you information of more than that, right? And you need to know for each one of the tokens which kind of named entity label it should have. So yeah, self-attention on its own cannot do that. But then when we, if you now are thinking, okay, if named entity recognition is useful to do these extra tasks where you are interested about relationships, then you are right that the fact that there is self-attention helps transformer-based models do all of these, downstream tasks that we are interested to use the outputs of NER or part of speech tagging for. So I think that's the kind of connection you're making, but you can't use self-attention just for sequence labeling, but you can use it in transformer. Any questions? No? Okay. Okay, so now we learned two sequence labeling tasks, part of speech tagging and named entity recognition. And I mentioned that there is a supervised machine learning approach that doesn't rely on neural networks that we can deploy for these two tasks. And it's called hidden Markov model. It is a probabilistic sequence model, which means that given a sequence of units, which can be words, letters, morphemes, sentences, whatever, it computes a probability distribution over possible sequences of labels and chooses the best label sequence. Can you recall when we talked about Markov before? And when did we last calculate the probability distribution of some potential sequences? Yes, please.
It was Markov approximations or something.
We mentioned Markov assumption, and yeah, where did we use it?
For generating sequences, right?
For generating sequences. And how do we call that? Yes.
Statistical language.
Yeah, you both are right. So we use this, we introduced Markov as a person, as a mathematician for the first time when we talk about statistical language models, like language modeling, the task of predicting the next word. So here again, with language modeling, you have a sequence and you're producing another sequence, or given like a shifted input, you are trying to, predict what comes next. You're kind of labeling, with the next word is funky way to think about it. And then what we got out of the statistical language models is the probability, by using the Markov assumption, is the probability of the whole sequence. So for a given sentence, we had the probability of that sentence being generated under the model. And I never really introduced this super formally, but what's behind this in mathematically so-called discrete Markov chain? It consists of n states, which later on we will make a distinctions between states and observations. Here, states and observations are the same thing. And formal way to think about what are the states. These are random variables which can take on values from some set. Remember, Markov was a mathematician, and this was all used in introduced in the context of random variables. Then for Markov chain, we are gonna just go over the components of a Markov chain. So you need a transition probability matrix, commonly in NLP denoted with A, which represents the probability of moving from one state to another state. So if you are doing language modeling, moving from whatever history you have so far to a next state, which will be previous state plus additional word. It put it in the matrix, which means that if we have kind of probability, we want to have a probability distribution of moving from one state to all possible other states. And that means that the sum of each row should be 1. We also have some kind of initial probability distribution, which tells us the likelihood we are going to start in a given state. And some, states might not be options, so they might have 0 probability. And then we deployed what has been mentioned, which is the first order Markov assumption, where we assume that the probability of being in certain, the next state taking on certain value depends only on the value of the previous states rather than on the previous, on the entire previous history. So we kind of informally talked about all of this. This is just more formal way to, introduce a Markov chain, a Markov assumption. And now this is Markov chain, and we talk about, we never really mentioned hidden Markov models. So what's the difference between like Markov chain and hidden Markov model? And maybe immediately to you, this word hidden becomes a thing that sounds unique, right? And if so, you would be right. So hidden here refers to the fact that we do not observe states, meaning states are, we say, hidden or latent. So for example, with part of speech tagging, we observe words. Those are observations. But if we deem part of speech to be states, these hidden states, then we do not observe them directly, but rather infer them from words. In that sense, they are hidden or latent. So when we deal with that kind of situation, you should be thinking about these hidden states stochastically emitting the observation. So given a hidden state that is, connected to some part of speech, you are going to produce some kind of observation, which would be actual word. Which means that we need to introduce another component to Markov chain to have hidden Markov model. And that's going to be this matrix of emission probabilities, each expressing the probability of an output observation, for us words, to be generated from a hidden state, where hidden state refers to unobserved part of speech tag. Besides Markov assumption with hidden Markov models, we are also going to make another assumption, and that's output independence, which means that the probability of an output observation word will depend only on the state that produced the observation and not on any other states or any other observation, which will come handy later on. So just to kind of show you this toy example, here we have three possible parts of speech tags. And we mentioned there are these emission probabilities. These are probability that a certain word will be generated given a certain part of speech tag. So think about it as conditional probability of a word given a tag. So these are going to be emission probabilities. Emissions coming from this idea that given a state, you are stochastically emitting observation, which are words for us. Then we have our transition probabilities. Our states are the part of speech tag. So it's basically a probability of going from one part of speech tag to another. This should be kind of intuitive. We have already previously said that if you have a certain adjective, let's say right now, it is likely you might have a noun next in English language. And then there are some initial probability, which tells us in which kind of part of speech we are going to start our sentence with. For example, determiner is a very common way to start a sentence in English language. So what happens? We start with some special start word. And we, based on our initial distribution of a possible part of speech tags, we have decided that the first state is going to be referring to determiner. And then given that we have determiner right now, we are going to emit stochastically a word, giving the emission probabilities. So here, determiner, the high probability is that the word that's going to be generated is the. So that's what we kind of ended up stochastically randomly producing. And then again, we have our transition probabilities, like what is the next state? Well, the next state, likely state, is to be noun, and given a noun, here we can see that interest is a very highly probable word to be emitted, but because this is a stochastic process, we randomly sample a lower probability word. So this is the kind of like what is happening conceptually behind a hidden Markov model. Okay, let me see. We don't have a ton of time, but I do want to stand up on a. All right, let me go over this. This is my last slide. So with the hidden Markov model, we get a sequence of words and a sequence of tags. We are trying to find a sequence of tags that is going to maximize the likelihood of the tags given the words. And if we use Bayes' rule, we can rewrite this. We can change the conditional probabilities. When we do that, we can also observe, well, this denominator doesn't really depend on the tags, so the maximization over possible tags is going to be the same regardless of what's in denominator. So we can remove it and deploy our assumptions. Markov assumption that here we deploy the Markov assumption that the current tag depends only on the previous one. And we can write the joint probability distribution as the product of conditional probabilities, right? We have deployed this many times in the course. So we can use this. And we have now introduced in the output independence, and we deploy it over here, that the conditional probability of the word depends only on the previous state, which is a tag for us. And now you can actually use what you have introduced already. You have introduced matrices A and B, and what these probabilities are basically values of matrices A and B. And here, what these probabilities is just the initial probability for that state. So this is how we are, this is the hidden Markov model. What we did not talk about is how do we find those values, these conditional probabilities, right? So this is what we are going to talk about next. What are going to these probabilities be? And then you can plug those values into this equation to find your best sequence of tags. But we are going to see that that's really slow, and then we are going to talk about how to do this inference faster and more efficiently. Okay, thanks for being patient with all the technical issues, and see you on